32 terabytes. Right off the bat, just let that number sink in for a second. That is the staggering amount of GPU memory required just to hold the weights, the gradients, and the optimizer states of a 2 trillion parameter AI model. I mean, we're talking about needing 400 H100 GPUs just to park the data, and that is before a single solitary calculation even occurs. But look, holding the data, that's literally just the warm-up. Once the actual compute kicks in, the training process demands an absolutely mind-boggling number of calculations. 4.8 times 10 to the 26th floating point operations, to be exact. This scale of math doesn't just push standard computing to the limit, it fundamentally breaks it. To really put this into perspective, if you took a single state-of-the-art H100 GPU and ran it at half its theoretical peak capacity, it would take over 30 millennia. Yeah, 30,700 years to process those operations. So unless you've got a time machine hiding somewhere, we have a major problem. So welcome to this explainer. Today, our goal is to uncover the impossible blueprint behind training these massive frontier models. We're going to look at the incredible software cheats, the brilliant workarounds, and honestly, the sheer engineering miracles that researchers are using right now to conquer these unyielding physical constraints of time, memory, and hardware. Okay, let's dive into this. We're going to logically break down this chaotic math into a structured journey. We'll start with the sheer scale of the problem, figure out how to break the memory wall, solve the parallel processing puzzle, compare Meta's Llama 3 with DeepSeek, and finally, look at how engineers survive the absolute chaos of hardware failing mid-run. So, moving right into section 1, the scale of the problem and the literal physics of 2 trillion parameters. If we look at the brute force math behind the curtain, we run straight into a compute optimal rule created by DeepMind called the chinchilla rule. It dictates that you need roughly 20 tokens of training data for every single parameter. For a 2 trillion parameter model, that means processing 40 trillion tokens. When you add up the 16 bytes needed in memory per parameter, the minimum 400 GPUs, and the massive time required, the brute force compute bill lands near $750 million for just a single training run. So the crucial takeaway here is that no team has ever actually paid this theoretical bill. They literally can't. They have to find workarounds, which is exactly why the AI industry is evolving at breakneck speed today. Which brings us to Section 2, breaking the memory wall, and the sheer magic of squeezing 32 terabytes into 80 gigabyte chips. Now, the traditional way to train AI is something called data parallelism. You copy the entire model onto every single GPU, split the training data into shards, and let them go to work. But wait, we just established our model state is 32 terabytes. Replicating that onto every single 80 gigabyte GPU is physically impossible. On top of that, there's a hard limit to how much you can just crank up your batch size before the math stops actually helping the model learn. So you have to ask yourself, how do engineers actually fit the model without bringing the massive cluster to a grinding halt? Enter our first hero, ZRO. That stands for the Zero Redundancy Optimiser, created by Microsoft's DeepSpeed team. Instead of duplicating the entire massive 32 terabyte model onto every single GPU, Zero brilliantly shreds the model state into pieces. It partitions the optimizer states, the gradients, and finally the parameters themselves across the entire cluster. So no single GPU holds the complete model. Instead, each GPU pulls in exactly the pieces it needs, exactly when it needs them, does its math, and then throws that temporary copy away. It's an incredibly clever workaround that perfectly fits this massive model well inside a single GPU's budget. Now let's move to Section 3, the parallel processing puzzle, and see how this builds into our next massive challenge, wiring the cluster. Think about it. If tens of thousands of GPUs are working on different shards of data, they eventually have to average their findings together to update the overarching model. But funneling everything back to one central machine, that would create a crippling bottleneck. The solution here is a highly elegant algorithm called ring-all-reduce. Imagine a massive factory assembly line arranged in a circle. The data gets split into chunks, and simultaneously, every single GPU passes a chunk to its right neighbor while receiving one from its left. Over a series of steps, they're constantly adding these numbers together. By the end of this highly coordinated bucket brigade, every single GPU holds the exact fully averaged data, all without melting down a single network cable.
But ring-all-reduce is just one piece of an entire arsenal of parallelism tricks engineers have to use. They use tensor parallelism to literally slice up matrix math across multiple GPUs. They use pipeline parallelism and 1F1B scheduling to fix these annoying idle bubbles where one GPU is working furiously while 15 others just sit idle waiting for data. And they use context parallelism, like ring attention, to handle massive million-token sequences. All of this complexity exists because of one brutal physical constraint. Moving data between different servers results in an 18-fold speed drop-off compared to moving data inside a single server.
And this constraint sets the stage perfectly for Section 4, Llama 3 versus DeepSeek. This is essentially a high-stakes engineering showdown between two completely different strategies for winning the compute war. Take Meta's Llama 3. It's built on a massive, dense architecture running on a totally luxurious setup of over 16,000 top-tier H100 GPUs. Because they have ultra-fast NVLink connections inside their servers, they can comfortably use a tensor parallelism of 8. Now contrast that with DeepSeek v3. They faced a much more constrained reality, working with 2,000 older H800 GPUs. And this brilliantly illustrates how DeepSeek just abandoned tensor parallelism entirely. Why? Because it was simply too expensive and slow over their restricted network paths. The architectures themselves couldn't be more different. Meta leaned into a brute force dense architecture. That means for every single word or token processed, all 405 billion parameters activate and do the math. DeepSeek, on the other hand, went with a mixture of experts, or MOE. Out of their massive 671 billion parameters, a clever internal router only picks the top experts for any given token, so only 37 billion parameters are actually active at a time. They even designed a smart routing bias that gently nudges tokens toward underused experts, perfectly balancing the workload across the GPUs without relying on traditional auxiliary losses, which, by the way, are basically extra training penalties that can actually degrade the quality of the model. So what does this smart cost Mu architecture actually achieve? Remember that $750 million brute force bill we talked about at the beginning? DeepSeek's clever, highly optimized training cost came in at a mind-blowing $5.6 million. That is roughly 130 times less. It is a stunning, absolute victory of software optimization over sheer hardware limitation. But, no matter how amazing your software is, physics always catches up. Welcome to Section 5, Surviving the Hardware Chaos, or what happens when thousands of GPUs inevitably just break. The data from Meta exposes the messy, chaotic reality of training these beasts. During Meta's 44-day training run for Llama 3, the supercluster experienced 419 unexpected failures. Think about that. That is a breakdown roughly every 3 hours. 30% of those were GPU or hardware link failures, 17% were memory failures, and the rest were network and software crashes. When you push this much hardware to its absolute limit, 24/7, for months on end, it literally just starts melting down. If engineers had to go in and fix these manually, the model would never finish training, ever. So they built an absolute duct tape miracle, an automated recovery pipeline. The system saves the full training state to memory every 5 minutes. When a failure happens, anomaly detection pauses the task, diagnostics instantly identify the fault, and Orchestrator magically swaps in a hot, waiting spare GPU, and training just resumes from the latest 5-minute checkpoint. Thanks to this automated 4-step process, only 3 of those 419 incidents actually required human intervention. That gave Meta an absolutely staggering 90% effective training time, despite the constant hardware deaths. So, let's pull all this together and look at how this is shaping the future. We are moving rapidly toward hardware-aware co-design, building our algorithms specifically for the physical layout of the chips. Look at NVIDIA's new GB200 racks. They pack 72 chips acting as one massive mega GPU, pushing bandwidth to an insane 130 terabytes per second. That could potentially make complex pipeline parallelism completely unnecessary. And new frameworks like DLO are already proving we can synchronize gradient updates across data centers 1,000 kilometers apart. For you and me, this means the next generation of AI is going to be vastly more powerful and far more accessible. It's crazy to think that just 5 years ago, almost none of the techniques we discussed today even existed. Every single time we hit an unyielding wall of physics, human cleverness finds a way to shatter it, shred it, or just rote right around it. Which leaves us with one final thought. As these physical constraints continue pushing us to fundamentally rewrite the very rules of compute, what impossible blueprint will human ingenuity draft next? Thank you for joining me on this explainer, and definitely keep your eyes on the frontier.